I run in this series of heat loss through double pane window, that is example 3.3 taken from the heat transfer essential book. Here is statement of the example. Consider a 0.8 meter high and 1.5 meter wide double pane window consisting of two 4 mm thick layers of glass whose thermal conductivity is 0.78 watt per meter Kelvin, separated by a 10 meter wide stagnant air space, and its thermal conductivity is 0.026 watt per meter Kelvin. Determine the steady rate of heat transfer to this double pane window and the temperatures of its inner surface for a day during which the room is maintained at 20 centigrade while the temperature of the door is -10 centigrade. The convection heat transfer coefficients, the inner and outer surfaces of the window to be H1, that is 10 watt per meter square Kelvin, and H2, that is 40 watt per meter square Kelvin, which include the effect of radiation. This is a double pane window. This is the first layer of the glass, this is the second layer of the glass, and in between these two glasses there is the stagnant air, which conduction heat transfer is occur, not convection heat transfer. Remember, to this air we are consider the heat transfer that is occur through it, that is conduction heat transfers, not convection. Normally through air convection heat transfers occurs, but in this case it's heat transfer that is occurred through the air is conduction. Why? Because it is stagnant, and for stagnant air we assumes conduction heat transfers. Now let me write the data. This temperature 20 centigrade. This temperature 20 centigrade is the inside temperatures of the room, let's say T infinity 1, and this is the outside temperatures of this double pane window, that is T infinity 2, and it is -10 centigrade. The temperatures 20 centigrade drop to T1, then T1 to T2, then drop to T2 to T3, and then T3 to T4, and finally it reached to -10 centigrade, the outside temperatures of the double pane window. The thickness of the glass is 4 mm, and the thickness between two layers of the glass is 10 mm. In between this 10 mm thickness, a stagnant air is provided, and then second layer of the glass thickness is also 4 mm. So it means the resistance that is offered to the heat transfer at this glass and this glass is the same. So let's come toward the data that is provided in the statement. First thing that is given is the height of the window, is 0.8 meter, and the width of the window is 1.5 meter. Then surface area for this double pane window will be 0.8 by 1.5, and you will get the area, that is the thickness of the first layer is L1, that is 4 mm, convert into meter, multiply with 10 to the power -3, and you will get 0.004 meter. And the thickness of this layer in which stagnant air is present, that is 10 mm. So we will see L2 is equal to 10 multiply 10 to the power -3. So we know that 1 milli is basically equal to 10 to the power -3. So that's why we multiply it with 10 to the power -3, and it will be converted into meter, and it is equal to 0.01 meter. The thickness of this layer is LE, and it is 4 mm also. We can say 0.04 meter. So it is 0.004 meter. Thermal conductivity of the glass is given, that is 0.78 watt per meter Kelvin. The thermal conductivity of the air is low, as you already know, that is 0.026 watt per meter. Convection heat transfer coefficient at the inside of the double pane window is H1. The convection heat transfer coefficient at the outside of the double pane window is H2. The inside temperatures of the double pane window is infinity 1, it is 20 centigrade, and the outside temperatures of the window -10 centigrade. Let me write the thermal resistance network diagram for this double pane window. Let me start from the temperatures at the inside of the double pane window. This is, let's say, T infinity 1. Temperature drop from infinity 1 to T1. It means that there is some resistance that is offered the heat transfer, and that is, let's say, Ri. It is the Ri means the inside of the window. This is Ri, and the temperatures drop to T1. Then temperature drop from 1 to 2. Slight temperature drop is occur, and in this case the resistance that is offered the heat transfer is by this glass. This is, let's say, R1 first, then temperature drop from T2 to T3, and in between the resistance it is offered is, let's say, R2. This resistance that is offered to the heat transfer by the air, that is R2. Next is the resistance that is offered by the second layer of the glass, that is R3, and the temperature drop from T3 to T4, and finally temperature drop from T4 to T infinity 2, and that is -10 centigrade. Resistance and they offer from T4 to T infinity 2 to the heat transfer is R0. We write thermal resistance network diagram in such a way that you can clearly understand. This is the thermal resistance network diagram, and the most appropriate in a clear way. I have written, so you don't get confused with it. Now come toward its solution. Look at this thermal resistance network diagram. The first resistance that is offered to the heat transfer is Ri. This is the inside of the double-pane window, and this resistance that is offered to the heat transfer is by convection heat transfer. So that's why we can say that it is equal to 1 divided by H1A. What is value of H1? That is given, and I have already written, that is 40, that is 10 watt per meter square Kelvin, and multiply the surface area, it is 1.2. Calculate that calculators. You find this on calculators. This resistance R1 is offered by this first layer of the glass, and the mode of heat transfer in this glass is conduction. Then we can say that R1 is equal to L divided by Ka, and this glass is the same in terms of thermal conductivities and thickness. That's why it is also equal to R3. So it means that R1 and R3 are same, and its value is L divided by Ka. What is the L value? That is 4 mm its thickness, and 4 mm in terms of meter is equal to 0.004 divided by thermal conductivity of the glass, that is 0.78, and the surface area, that is 1.2. Solve this on calculators. You will get the R1 and R3 value, it is 0.00427 centigrade per watt. This is to find the resistance R2. The R2 resistance is also L divided by Ka. What is L? That is thickness, that is 10 mm. To say 0.01 meter divided by K. Value of K for air is 0.026 and area is 1.2. Solve this on calculators. You will get the R2 value, and it is 0.3205 centigrade per watt. This is to find the R0, the mode of heat transfers outside the panel, convection heat transfer. In this way, we can say that the R0 value is equal to 1 divided by H2A. It is 1 divided by, what is H2 value? Outside the double-pane window, it is 40. Surface area is 1.2. When you solve on calculators, you will get the R0 value is 0.0208 centigrade per watt. The total resistance that is offered to the heat transfer is equal to Ri plus R1 plus R2 plus R3 plus R0. Is the Ri value, that is 0.0833. R1 value and R3 value is the same, that is 0.00427. And the R2 value, that is 0.3205, and the R0 value is 0.02083. Simply add this and you will get the total resistance that is offered to the heat transfer, and it is 0.4332 centigrade per watt. The rate of heat transfer is equal to change in temperatures divided by the total resistance that is offered to this change in temperatures. Change in temperatures T infinity minus T infinity 2 divided by R. And just simply enters the value. It is 20 minus, and outside temperature is minus 10 centigrade, divided with 0.433, where you will get 30. Minus become plus, divided by 0.433, and you will get the rate of heat transfer loss to this double-pane window, that is 69.2 watt. This is our answer.